that more advanced than what we just talked about?
Sorry, what's that?
Is that more advanced than what we just talked about?
Not too much. It's more advanced than I will tell you the guarantee problems will be.
Okay.
Guarantee problems will be two objects colliding, closed system.
Okay.
So for the sakes of this class, if I understood this correctly, we're always gonna have a closed system.
No, but it should be obvious when reading it whether it's closed or not.
Okay. So they're, okay.
In the collision problem, I think you can probably be guaranteed it's gonna be a closed system. But recognize it's not always a closed system because I talked about impulse. Impulse is equal to the change in momentum. So it is possible to change momentum if there's an impulse. Some external force being acted on the system for a certain amount of time. We'll get there. I have a 5 kilogram box and a marker that doesn't want to roll. To the landfill you go. 5 kilogram box, cruising along at 3 meters per second. I'm putting a little 5 there. This is just something I do. I like the subscript to have some meaning with the object itself, and so I did 5 just because it's a 5 kilogram object. If you want to call it piece of 1 because it's the first one, or just P because there's not another one, there will be in a moment. Go for it, but I'm putting a 5 here just to indicate it's the 5 kilogram mass. That's just my personal notation. So, what is the momentum of this object at this moment?
5 times 3. Velocity.
Mass times velocity.
Okay.
So 15 meters. Wait, no. Is there a unit for this? Oh.
Kilogram
Times per
meters
meter
over
squared.
seconds.
There you go.
Sorry, what'd you say?
Kilogram meters over seconds.
That's about, I think it was like kilograms per meters a second.
Yep. Kilogram meters per second.
Does it have a different, like, do you?
It does not.
Okay.
Because apparently they're fine with doing this. But Newton meter, no, it has to be a joule. Now, recognize also that if we look back at the impulse formula, impulse, which is the integral of F dot dt, not a dot product, F dt is equal to the change in momentum. The units of F times time must be equal to the same units of momentum. And so this is a Newton second. And this is a kilogram meter per second. So you could also do 15 Newton seconds, which some people prefer.
I like that. Will you accept that?
Yeah, that's
Yeah.
perfectly legitimate. And you have actually a third choice. For the vanity in you.
Okay.
I get to make up my own unit. Now, I can't just make up the unit and assume everyone knows what it is, and I can't say that, well, I wrote it down once, so therefore you should know it for the rest of your lives. No. Every test, you would have to do it, or quiz, or whatever, you would have to define this. Now, I tend to use a D for that, because we don't use D for anything else. Whatever you're using, don't use a unit that we're already using. For example, don't use a capital J. Your name is James, and you feel like, hey, I want to honor myself, do not use capital J. You're using So I can define D, so the 3 equal marks is, by definition, a kilogram meter per second. And so at that point, once this is defined, I could also write this as 15 Descartes. Rene Descartes did some thoroughly work in this.
Wait, so
So
is
essentially,
that-
we could literally put whatever unit system we define.
Yeah, but you have to define it
Right. I get
each assignment.
So,
I didn't know.
so is that applicable for like everything? Like, if I wanted to if I was doing a velocity problem, and I wanted to assign a unit for velocity, and I didn't want it to be meters per second?
Yes, yes, you can. Again, don't use letters that are already being used. And it doesn't even actually have to be a letter. You could come up, I had a student a couple years ago who did a little pumpkin. Why, I don't, jack-o'-lantern. Just cause.
They're mad at jack-o'-lantern.
You got tired of writing meters per second, so they drew out Jack.
Tired of writing kilogram meters per second.
Oh, oh.
Now, if I erase the board and I erase that top corner first, as soon as I erase that, this is now wrong, because this is not a standard unit, therefore it only is valid as long as it's defined. I will stick with sort of the computer science way of defining things. If you put it at the very top of a master set or test or whatever, I'm assuming it covers the entire test. If you put it for just a single problem, it's a local variable, and I assume it only covers that problem.
To me.
All right. Is this correct?
I wanna say
Yes.
yes.
Looks good to me.
There's probably more to it. No.
We're assuming it's a closed system, so yes.
It's just the only, that's the only object there, there's nothing, no forces acting on it. All right,
Oh, there's not.
adding to this closed system, so now there's a second object. We'll make it 2 kilograms, going at 4 meters per second. So the momentum of the 2, and I'll just go ahead and stick the I in there, because they're gonna hit each other.
No.
What is the momentum of this object?
8 Newton seconds. Yeah.
8D.
And again, when you're putting multiple units like that, put a dot in between just to indicate that it's not part of the same thing. Well, I'll tell you right now, one of those is wrong.
Oh, wait.
So then one of them's right.
That is true, that is true.
That,
Oh, would it be,
Oh, it's negative.
yeah.
oh, 'cause
Which
it's
one's negative?
the one going in the.
It depends on which
Oh,
way we
wait, we
decide
have to
the
define the direction.
direction.
Which way do you want to make positive?
To the
That
right.
way.
Rule breaker.
So I could not identify whether this was really right or not, or I could have gone with the assumption of, well, I guess you've now defined what the positive direction is.
It's always to the right.
But now that becomes negative. They are in opposite directions. Momentum is a vector. Direction matters. Right, one other thing here. It is difficult to really communicate this when I'm writing it on the board. Textbooks are much easier. Typically, a capital letter represents the momentum for an entire system. A lowercase letter represents an individual one. I don't really stick with that because my big P's and lowercase p's basically look the same. So this is supposed to be a capital P here, those are supposed to be lowercase p's. Not that you can really tell. Those are capitals.
Oh,
That's a lowercase.
On a test, would you like?
I don't care, but if you're reading a textbook and you see a capital P one place and a lowercase p another place, the capital P is generally the momentum of the entire system, lowercase is just individual.
Yeah. Yeah, sure.
So what is the total momentum before they hit each other?
7
7 newtons per second.
Newton seconds.
It's disease.
Do it.
It's not newtons per second.
Newton seconds?
Yeah.
Newton seconds. Oh, Newton.
Ed was a student I had a couple years ago, whenever he did more than one unit, per was always thrown in between them.
I guess
It's
that's
a divider.
I guess that's what
And that means that the final would have to be 7 as well, because we're not, I mean,
So what's my final? What's the P final?
7 Newton seconds.
Yep,
So it's Newton seconds?
Newton seconds.
Newton seconds.
So-
Or Descartes or kilogram meters per
Oh,
second,
okay.
or whatever you want to create your own.
Can we do one where we throw something in there to like throw it off, like make it so it's not like the same?
Like a third object?
Yeah, like a third object, yeah. Like not a close.
Wait, is that like the
You
test
just-
problem?
you're-
Super-
you're
I'm
the
trying,
masochist?
I'm trying because you said.
let's.
Yeah, all right, so I have done problems like that where you take a missile or some projectile, you launch it in the air, while it's in the air, it explodes into 3 pieces.
Yeah,
I mean, that is the type of problem where you now have the earth in, taking the earth into account.
Cause I always find myself on your tests, like I'll look through them and I'll be like, do I know, is there anything on here that like I may have forgotten to ask him or like I wasn't expecting? And there's always something like that. I'm trying to make it so there's nothing like that.
Okay, but let's, maybe, when we get there, we can talk again, but, you know, right now, let's just keep it simple.
Okay.
Did you have a question?
You had said something about this was gonna be similar to a test problem. Is this similar to it, or are you just trying to show us how the initial momentum is equal to?
The test problem would be, I have a 5 kilogram mass going to the right at 3 meters per second. I have a 2 kilogram mass going to the left at 4 meters per second. They will collide in and I'll specify what type of collision. What is the final velocity, or what are the final velocities?
Sorry, how does the collision affect your answer?
Oh, it doesn't.
Oh,
No, so on the test, you're gonna ask for final velocity.
Yeah.
Okay.
All right, so let's talk about the different types of collision, because these things, two things could happen. One, they stick together, or two, they bounce off each other. So, let's deal with, let's say they stick together. Otherwise known, what I will call a perfectly inelastic collision, or PIC. There's a video. Have any of you seen the naming convention video?
mm-hmm.
Oh,
Yeah, we're gonna go over some of it now, but please, if you haven't seen it, please make sure you watch it again.
what chapter is that in?
Chapter 10,
Oh, okay.
I think momentum's 10 and 11.
I have not looked at that
If they stick together, I know my final momentum is 7 Newton seconds. Positive. And that's gotta be equal to the momentum. Well, that is my momentum. So that's mass final times velocity final. Because it's now one object, you can treat it like it has two objects with the same final velocity, or one object with a final velocity.
Well, the mass would be 7, wouldn't it?
Yeah.
And then you could solve for velocity off of that.
Wouldn't it be 1?
Give me the whole thing.
It's 1
Meter
meter
per
per second.
It is a positive answer, which tells me when they collide, it's gonna be moving off, they'll still be moving to the right.
So because velocity final and velocity both final velocities of the two objects are the same because they're sticking together, that's why you can say the velocity final is 1.
Yes. So, one of the questions on that last test will be the perfectly inelastic collision, and the question will be, what is the final velocity, singular?
It's not that bad.
Pardon?
That's not that bad. I thought it was
No.
gonna be worse than that.
It's not bad.
About the elastical.
Yeah, we'll get to the elastic. Oh, by the way, naming convention, I call this perfectly inelastic collision. Some textbooks will just call it, perfectly inelastic collision. Some textbooks will just call this inelastic collision. Some textbooks, for them, inelastic means they stick together. For other textbooks, just saying inelastic is not enough. Just saying inelastic means that some kinetic energy was lost. In the cases where the textbook says an inelastic collision just means kinetic energy is lost, they would call this perfectly inelastic. In textbooks which would call this an inelastic collision because they stuck together, the ones where there's just loss of kinetic energy but they don't stick, we'll call that the elastic collision. And just to make it more confusing, the textbooks which call they hit bounce off each other, kinetic energy is lost. Those who call it inelastic would call the kinetic energy conserved problem elastic. And those who call where kinetic energy is lost but they don't stick elastic would call the one where kinetic energy is conserved as perfectly elastic. And frankly, I use so many different textbooks, I cannot keep track of which author is doing which. So I hope to have simplified it by coming up with another naming.
If you can't beat them, join them.
Perfectly inelastic, they stick together. Perfectly elastic, kinetic energy is conserved. So the perfect serve the two extremes. Kinetic energy has maximal loss, inelastic, perfectly inelastic, perfectly elastic, kinetic energy is conserved, and anything in between, imperfect. And I'm sorry, I cannot remember which your textbook uses. I gave up trying to keep track.
Well, we have cases where it's imperfect.
Yeah, the imperfect ones, depending on what kind of foul mood I'm in. The imperfect ones, I will often just say set up the equation. You don't actually have to solve it, or set up the equations. However, questions on this before we take a look at the kinetic energy of our problem here? All right. K5 initial. What is the initial kinetic energy of this mass?
22.5. Oh god, joules.
Generally just joules, but oh god, joules maybe. And the initial kinetic energy of this guy.
Same thing. Oh, well, yeah.
Just 16.
Yeah, I think it would just be 16.
2.
I'm just getting 16.
2, 4.
Are these these are independent, we're not, this isn't the collision, this isn't the.
Right, this is the two separate.
My mistake.
8.
So my total initial kinetic would be,
38.5 joules.
how'd you get that?
You add them, now wait. Oh. Am I doing that wrong?
Then it is here?
When you subtract them,
Why would you subtract it? Because one's negative?
yeah.
Don't forget, kinetic energy, you'd speed squared. So even if you did the -4 squared, you still get a positive
That
number.
makes sense, yeah.
Despite what some students have tried to convince me otherwise. You might have said it, I might have just misheard.
38.5 joules.
Yeah,
Oh, you just add them together.
yeah, just that, my total is just the sum.
Yeah, you asked me that and I thought I did something wrong.
What I heard you say was 838,
Oh.
and so that's why I got confused.
Ah, okay.
I thought you multiplied them, but multiplying them wouldn't get that high. Yeah, total is just sum. Afterwards, I don't know why I picked up a marker. My total kinetic energy afterwards, I got 1/2 times my mass now, which is 7, times my speed squared. Ooh, I can do this one in my head. So we had a definite loss in kinetic energy. What does that tell us?
An impulse happened.
From the kinetic energy, we can't make a determination on impulse.
Does that mean that the objects, when they collided, absorbed.
They stick together? They stick together.
Well, they did stick together in this case.
Yeah.
Where did the energy go?
Into the other one? In the,
Non-conservative?
Pardon?
Is it non-conservative?
All right, so there's a change in kinetic energy, so there's definitely non-conservative forces involved here, non-conservative work being done. What's the non-conservative force involved here? These two things hit, what's the non-conservative force?
is there friction? I mean.
Them pushing against each other?
Yeah,
Them trying to
Normal
push each
force?
other and the other, oh, okay.
normal force. It's a normal force, it's the non-conservative force
Yeah.
here. But where did it go? And I started to hear a couple people sort of start down a path and then veer off. Where did the energy go? Energy is not conserved because there's non-conservative work being done.
We went into the other object.
How's it manifested? There are two catch-all responses to where did the energy go?
Did we lose it? Because the law of entropy can't use it anymore.
Entropy doesn't usually work that fast. All right, so spoiler, the two generic answers, sound and heat. If two things collide and there's sound, that means that some of the energy got transported into the air, which eventually you hear sound. And they also, in this case, even if we did this in a vacuum and they stuck together, the two objects would become hotter. Noticeably, it's not a whole lot of energy, ultimately.
How would that happen? I don't understand. Because of friction.
The kinetic energy goes into, so if I've got, just think of this as a ball, I've got a ball here and I smack into it. That ball will start moving faster. So if I take two objects and collide them into each other, the molecules in it will start vibrating faster. So in essence, the kinetic energy gets absorbed into the molecules themselves, which will vibrate faster, which we recognize as heat or higher temperature.